Hello. So this is lesson 3.5, and we're going to be talking about rational functions and their graphs. This is a longer lesson, so if you need to pause and come back to it or whatever, of course, always feel free to do that. So first, we're going to go ahead and define rational functions. And rational functions are quotients of polynomial functions. So this means that rational functions can be expressed as f of x equals p of x over q of x, where p and q are polynomial functions and q of x cannot equal 0. That is an important part to remember. We cannot divide by 0. Um, Also, to keep that in mind, the domain of a rational function is the set of all real numbers except x values that make the denominator 0. So let's look at an example here. Um, we need to find the domain of the rational function x squared minus 25 over x minus 5. So we know that x minus 5 cannot equal 0 because then we would be dividing by a 0. So what we're going to do is we're going to see what the x value is. So we're moving the 5 to the other side, and we see that x cannot equal 5. So we need to exclude that from the domain. And I'm going to show you two different ways to write the domain. There is a set builder notation. This is a set, so we're writing it inside braces, x, and a straight line. The straight line means is such that, so x is such that x does not equal 5. And that's the set builder notation. Now, the one that we've been mainly using is the interval notation, which is the negative infinity to 5 in parentheses on both sides because 5 is not included, or 5 to infinity. And again, 5 is not included, and infinity always has those braces around. Okay, let's look at another example. So find the domain of the rational function g of x. So we have x over x squared minus 25. Again, we know that the we can't divide by a 0, so the x squared minus 25 cannot equal 0. So we're going to solve for x to see what x cannot be. Adding 25, we get x squared cannot equal 25. We take a square root and remember to add the plus and minus. So x cannot equal positive and negative 5. So the same thing, set builder notation is x is such that x does not equal negative 5 or x does not equal 5 and close. Interval notation would be from negative infinity to negative 5. Again, negative 5 is not included, so parentheses, or negative 5 to 5, or 5 to infinity. So again, those are just two different ways of writing it. Okay, let's look at a third example here. So find the domain of the rational function h of x. Now, it needs to be so that x squared plus 25 cannot equal 0. Well, when we start subtracting, we get x squared does not equal negative 25. We take a square root and a positive and a negative again. We want to cancel that squared, so that's why we're taking the square root. X cannot equal positive or negative. Square root of 25 is 5, and square root of negative 1 is an I. Now, this is not a real number, so that means that we don't, there's no exclusions from the domain. If we look at x squared plus 25, it's always going to be positive because of the x squared, even if we have a large negative or a small negative number. So x is such that x um, is all real numbers, or negative infinity to infinity. Okay, next what we're going to do is we're going to look at arrow notations. So we're going to look at or write the symbol, and then we are writing the meaning of it. So our first one is going to be X arrow to the right, A and plus like in as an exponent. So what this means is that X approaches from the right. Next one is going to be X arrow A and a negative. And this means that X approaches from the negative numbers, so from the left. Next one is going to be X arrow infinity. So this it means X approaches infinity, that is X increases without bound. Okay, next one is X arrow negative infinity. So X approaches negative infinity, that is X decreases without bound. Okay, and where we're going to use these is what's called asymptotes. So um, the line x equals a is a vertical asymptote of the graph of a function f if f of x increases without bound as x approaches a. So what this means is that as x approaches from the right, f of x approaches infinity. And we can see that it is coming, like it's coming from the right and it's approaching infinity, going up. The right side, we still have the x equals a, but this is x as x approaches from the left. As we can see, it approaches from the left. F of x approaches infinity. Okay, same thing here. The line x equals a is a vertical asymptote of the graph of a function f if f of x decreases without bound as x approaches a. So as x approaches from the left, I'm sorry, from the right, it's going this way. F of x approaches, it keeps going down, negative infinity. Okay, same thing here. As x approaches from the left, it's coming from here. F of x approaches negative infinity. So an asymptote is something that the function keeps approaching, but it never touches or crosses it. Okay, now locating vertical asymptotes. If f of x equals p of x over q of x is a rational function in which p of x and q of x have no common factors, and a is a zero of q of x, then, or the denominator, then x equals a is a vertical asymptote of the graph of f. So what we're going to do, we have an example where we're going to find vertical asymptotes if any of the graph of the rational function f of x equals x over x squared minus 1. So first we need to check for common factors. So x is already factored. We can't factor it any farther. We're going to go ahead and factor x squared minus 1. And that, so we're going to set that to equal 0 to find the zeros. Add 1, so we get x squared is 1. We're going to take a square root, positive and negative, so we get x equals positive and negative 1. Now, we got the x's, so we got the zeros, which are 1 and negative 1. But now we can actually write this back as a factor. So since we have the positive and negative 1, f of x will be x over x plus 1 times x minus 1. So when we look at this form right here, we can see that no common factors in the numerator and the denominator. And we know that zeros of q of x are these two. So, are negative 1 and 1. So since those are our zeros, then our vertical asymptotes are x equals negative 1 and x equals 1. Okay, let's look at this next problem here. Again, we have h of x equals x minus 1 over x squared plus 1. Now, if we do the same thing here with the x squared plus 1, we're going to set it to equal 0. We're moving the 1 to the other side so it changes signs, and we take a square root to cancel the squared. We get positive and negative, and square root of negative 1 is an I. So this means that we cannot factor x squared plus 1. So that means that the denominator has no real zeros. And that means that the graph of f of x has no vertical asymptotes. So that's the vertical asymptote. Now we're going to go ahead and look at the horizontal asymptote. So now we have, so notice that vertical was x equals a. Now horizontal asymptote is y equals b. And again, if f of x approaches b as increases or decreases without bound, but it never touches it. So let's look at this first one right here. We have x, as x is approaching infinity, so it keeps going and going, f of x keeps approaching b. In the second one, again, x is approaching infinity, and f of x is approaching b. Okay, let's look at the third one. Again, as x approaches infinity, f of x approaches. Yes, there's a little bit of a, like it goes down, but then it does keep going up towards the approaches, b. Okay, locating horizontal asymptotes is a little bit trickier, and you've got to make sure that you remember. So if we have a rational function, um, the degree of the numerator is n, and the degree of the denominator is m. Make sure that you know those that difference. So if n is less than m, so the degree of the numerator is less than the degree of the denominator, the x-axis, or y equals 0, is the horizontal asymptote of the graph f. Now, if n equals m, so the degree of the numerator equals the degree of the denominator, the line y equals an over bm is the horizontal asymptote of the graph of f. So we are dividing the leading coefficient of the numerator by the leading coefficient of the denominator. And that will be the horizontal asymptote if the degrees are the same. Now, if the degree of the numerator is greater than the degree of the denominator, the graph has no horizontal asymptote. Okay, so let's look at a few examples here next. And we're going to use what we just learned. So f of x equals 9x squared over 3x squared plus 1. So our degree of the numerator is 2, and the degree of the denominator is 2. Now, we notice that 2 equals 2, so n equals m, which means that we are using this second one here. So we're going to take the leading coefficient of the numerator. So the leading coefficient of the numerator is 9, and the leading coefficient of the denominator is 3. So 9 divided by 3 equals 3. So y equals 3 is the horizontal asymptote. Okay, let's look at g of x here. Looks very similar, except if you notice the difference is the numerator degree. So now the degree of the numerator is only 1. Remember that there is an understood 1 right here. And the degree of the denominator is a 2. 1 is less than 2. So our degree of the numerator is less than the degree of the denominator. So that is number 1, which means that y equals 0 is going to be the horizontal asymptote. Okay, h of x. This actually has a mistake. This should be a 3 to the power of 3. So our degree of the numerator is 3, and the degree of the denominator is 2. So 3 is greater than 2, which means that n is greater than m. Now, if we look at n is greater than m, it says has no horizontal asymptote. It has a slant asymptote, but we're not going to go into that. But there's if again the degree of the numerator is greater than the degree of the denominator, we're just saying that no horizontal asymptote. Okay, next we're gonna first look at some basic reciprocal functions. So f of x is 1 over x. Now, we know that we cannot divide by a 0 here. So x cannot equal 0. So that has to be the vertical asymptote, which it is right here. If we look at the degree of the numerator and the degree of the denominator, the degree of the numerator is 0 and the degree of the denominator is 1. So we know that n is less than m, which means that y equals 0 is the horizontal asymptote, which it is right here. Okay, what we're going to do with this one is we're going to look at what happens if we plug in a negative x. So f of negative x, we get 1 over negative x, which is the same thing as negative 1 over x, which is the same thing as negative f of x. Now, this is an odd function since it is f of negative x equals negative f of x, and it has origin symmetry. We talked about these in the previous lessons. Okay, so let's look at f of x equals 1 over x squared. If we look at x squared cannot equal 0, so x cannot equal 0. So that has to be the vertical asymptote, which it is right here. For the horizontal asymptote, again, 1 is the numerator, so that means that it doesn't, or the degree of the numerator is going to be a 0. There's no x. Degree of the denominator is 2, so we know that the degree of the numerator is less than the degree of the denominator. So our horizontal asymptote is going to be y equals 0 in that case. So this one right here. Okay, we're going to do the same thing we did here on the other one and see what happens when we plug in negative x. So 1 over negative x inside the parentheses squared. This becomes 1 over x squared, which is the same thing as f of x. So we have an even function here. F of negative x equals f of x. And it has y-axis symmetry. Again, we could, if this was a paper and we folded it along the y-axis, the graphs would go on top of each other. Okay, next, we're going to look at transformations to graph a rational function. We talked about the transformations, and now we're going to go ahead and do that. And we are going to be graphing it. Let's see if there's enough room here. So we're going to begin with f of x equals 1 over x. So that's this one right here. Let me do a table here. We have an x, we have a y, 1 over x. So if we start, I'm going to plot 5 different points. So I'm going to do -2, -1, actually 6, a half, 1, and 2. Hold on, I'm missing a half. 1, and 2. Here we go. Let me, so that I don't. Okay, so 1 over x is going to be negative 1 over 2. 1 over negative 1 is going to be negative 1. Negative 1 over 1. 1 divided by negative half, we're flipping it, so it becomes a negative 2. The same thing with the half is going to be a 2. It's the reciprocal since we're dividing by 1 by it. 1 divided by 1 is 1, and 1 divided by 2 is a half. Okay, the first thing we're going to do now is we're going to shift 2 units left, and we are shifting x. So x minus 2. Remember, even though this is a plus, we are shifting it to the left. So this is a shift to left, and it's the x that we're shifting. So negative 2 minus 2 is going to be negative 4. Negative 1 minus 2 is negative 3. Negative half minus 2 is going to be negative 2.5. Negative, or half minus 2 is going to be negative 1.5. 1 minus 2 is negative 1, and 2 minus 2 is going to be a 0. Okay, so we shifted it first, and then we're going to go ahead and shift 1 down, and this is to the y. Let's make another, oops, that column did not go straight. So shift down. So we're doing y minus 1. So negative half minus half is going to be negative 1.5. Negative 1 minus 1 is negative 2. Negative 2 minus 1 is negative 3. 2 minus 1 is 1. 1 minus 1 is 0. And half minus 1 is negative half. Okay, so let's look at our points now. So x, y. So we shifted it x to the left, so it's negative 4. We shifted the y down, so it's negative 1.5. Negative 3, negative 2, negative 2.5, and negative 3. Negative 1.5 and 1. Negative 1, 0, and 0, and negative half. Okay. I'm going to go ahead and start graphing here. There's not a ton of room, but we'll get there. So 1, 2, 3, 4, 5. 1, 2, 3, 4, negative 1, negative 2, negative 3, negative 4, negative 1, negative 2, negative 3, negative 4. Okay, negative 4 and negative half. So negative 4, or 1.5, negative 1.5 is going to be right here. Negative 3, negative 2, negative 3, negative 2 is going to be here. Negative 2.5, negative 3 is right here. And then we jump to negative 1.5 and 1, which is right here. Negative 1 and 0, and 0 and negative half. Okay, so what would this look like? What we need to do next is we need to figure out the asymptotes. So first, we need to figure out the vertical asymptote. There we go. Okay, so our vertical asymptote in the original one is going to be x equals 0 because we cannot divide by x. Now, we shifted 2 units left. So that means that the asymptote shifts 2 units to the left as well. So x equals -2. We can double check. X plus 2 cannot equal 0. When we move the 2, we get x cannot equal -2. So x equals -2 is our vertical asymptote right here. Our horizontal asymptote in the original one, um, the degree of the numerator is less than the degree of the denominator. So it is going to be y equals 0. Now, what we did is we shifted it 1 down. So it's going to be y equals -1. Okay, y equals -1 is right here. Now we can see kind of where and what the graph does. And of course, this is just a sketch, so it's not an accurate, but we can see that, okay, that's where it keeps going and going. Okay, so we use transformations here to graph. Next, we're going to look at a strategy for graphing a rational function. So the following strategy can be used to graph f of x equals p of x over q of x, where p and q are polynomial functions with no common factors. So first, we're going to determine whether the graph f of f has symmetry. So we're going to calculate f of -x equals f of x if it has y-axis symmetry. And that means also that it is an even function then. F of -x is negative f of x. It means that it has origin symmetry and it is an odd function. So after we determine that, we find the y-intercept, if there is one, by evaluating f of 0. Step number 3, find the x-intercepts by solving the equation p of x equals 0. Find any vertical asymptotes by solving the equation. Remember, vertical asymptotes is the denominator q of x equals 0. And number 5, find the horizontal asymptotes using the rule for determining the horizontal asymptote of a rational function. Next, we're going to plot at least one point between and beyond x-intercept and vertical asymptote. And then 7, use the information obtained previously to graph the function between and beyond the vertical asymptotes. Okay, so our function that we are going to be graphing is f of x equals 3x minus 3 divided by x minus 2. Um, so what we're going to be doing is first we need to figure out or determine the symmetry. So what we're going to do is we're plugging in f of -x. So 3 times -x minus 3 divided by -x minus 2. -3x minus 3 divided by -x minus 2. So could we have some sort of symmetry? We can take the negative out, um, and we have 3x plus 3 on the numerator. We can take the negative out from the denominator as well, and we get x plus 2. So negative and negative cancel each other out because it is a division. So we get 3x plus 3 over x plus 2. Where, well, if you look at this, f of -x is not f of x, and it is not negative f of x. We took out the negative sign, but it actually canceled each other. So no y-axis or origin symmetry. Same thing, it's actually, it's neither odd or even. Okay, step 2 is going to be find the y-intercept. So we're evaluating f of 0. F of 0, plugging in the 0, 3 times 0 minus 3, 0 minus 2. So negative 3 divided by negative 2, 3 over 2. So our y-intercept is 0, 3 over 2. That is an improper fraction. We can write it as a mixed number, so it's a little bit easier to plot, which is 0, 1 and a half. Step number 3 is find x-intercept. So we're going to set p of x to equal 0. So the numerator, 3x minus 3 equals 0. We move the 3 to the other side. It becomes a positive. We divide by 3, and we get x equals 1. So our x-intercept is going to be the point 1, 0. Okay, let's actually start plotting these points. Okay, here's graph the function. So I'm going to go ahead and two, three, four, negative 1, negative 2, negative 3, negative 4, negative 5. Here we go. Okay, what were the points that we had? We had y-intercept 0, 1 and a half. So our y-intercept is going to be right here. 0, 1 and a half. And the other one was the x-intercept, which is 1, 0. So x-intercept is right here. Next step, step number 4, find the vertical asymptotes. So that was the q of x equals 0. So the denominator equals 0. Our denominator is x minus 2. So, oops, x minus 2 equals 0. So x equals 2. That is our vertical asymptote. So let's go and plot the vertical asymptote. X equals 2 is going to be right here. Okay, next we're going to find the horizontal asymptote. So if we look at our original equation, our degrees are 1 and 1. So 1 equals 1 are our degrees. So it's n equals m. So that was the one where we do the leading coefficient of the numerator, which in our case is 3, and the leading coefficient of the denominator, which is 1. So 3 divided by 1 equals 3. So our horizontal asymptote is y equals 3. We're going to go ahead and plot that y equals 3 here, right here. There we go. Now, next step is plot points between and each x-intercept and vertical asymptotes. So what we're going to do is we're going to do a table here, and we evaluate f at the selected point. So we're going to have x our y is 3x minus 3 divided by x minus 2. Okay, let's look at our asymptotes and our points. I would, because this is a 0, this is a 1, and then the asymptote is x equals 2, I would go to the left, the next point to the left as -1, and see what our y is going to be. 3 times -1 minus 3 divided by -1 minus 2. So -6 divided by -3 is a 2. So our next point is -1 and 2. -1 and 2 right here. Okay, then I would keep going to the right and take the x equals 3 and see what happens. So 3 times 3 minus 3, 3 minus 2. 6 divided by 1 is 6. So our point 36. Okay, 3, and this doesn't go up enough. 3, 6 is somewhere here. Next, I would see what happens with x equals 4, and actually I would take x equals 5 as well. So 4 and 5. 3 times 4 minus 3, 4 minus 2. So that ends up being 9 over 2, which is 4.5. So our next point is 4 and 4.5. I'm going to calculate 5 while I have this here and see. That one is going to be 12 divided by 3 equals 4. So 5 and 4. 4 and 4.5. 4 and 4.5 is somewhere here, and 5 and 4 is going to be somewhere here. Okay, now we can kind of see that it's starting to, so we have to remember that it does not cross the asymptotes. It just keeps approaching it on this side, and it does the same thing over here. Now, one thing that you can do, but just as a warning, or one thing that you can use is a website called Desmos, if you're not familiar with it. You can, graph these with Desmos. But again, a heads up, a warning, you're not allowed to use Desmos on the exams, but you can kind of play around with it. How does it look and what should it look and all that. So it's just kind of a tool to understand what it looks like. Okay, so we talked about the vertical and horizontal asymptotes, and now we're going to look at the slant asymptotes, which I already brought up a little bit. So the graph of a rational function has a slant asymptote if the degree of the numerator is 1 more than the degree of the denominator. So in general, if f of x equals p of x over q of x, p and q have no common factors, and the degree p is 1 greater than the degree of q, find the slant asymptote by dividing q of x into p of x. Okay, so let's look at this example, which we're going to, be finding this. So if we look at the degree of the numerator, that is a 2, and the degree of the denominator is 1. So looking at these two, 2 is 1 more than 1. So we know that there's going to be a slant asymptote. So what we're going to do is we are dividing q of x into p of x. So I'm going to use the long division here. 2x squared minus 5x plus 7 divided by x minus 2. So x goes into 2x squared 2x times. 2x times x is 2x squared. 2x times -2 is -4x. And now we're subtracting, so the signs switch. -5x plus 4x is -1x. 2x squared minus 2x squared is 0. We bring the 7 down. And 1x divided by negative 1x divided by x is going to be negative 1. Negative 1 times x is negative 1x. Negative 1 times negative 2 is 2. And then we flip the signs because we are subtracting. So 7 minus 2 is 5. And the x's cancel each other out. So what do we get here? We have, so 2x squared minus 5x plus 7 divided by x minus 2 equals, what's on the top here? 2x minus 1 plus, our remainder is 5. Our divisor is x minus 2. So our slant asymptote is going to be this one right here. We are ignoring the remainder, and our slant asymptote is y equals 2x minus 1. Now, I use the long division. You could do it with a synthetic division. You pick whichever one works for you. And again, this is only when the degree of the numerator is 1 more than the degree of the denominator when we get the slant asymptote. Okay, let's move on to application. So we have a company that is planning to manufacture wheelchairs that are light, fast, and beautiful. The fixed monthly cost will be $500,000, and it will cost $400 to produce each radically innovative chair. So write the cost function C of producing X wheelchairs. So C of X, our fixed cost is 500,000. So that is the cost that is going to be paid anyways. And then we add to it $400 per each wheelchair. So 400 times X. I'm going to write it in the correct format. So 400X plus 500,000. So it's a little bit easier. That is our cost function. Now we're going to write the average cost function of producing X wheelchairs. So average cost function, we're going to put a bar over the C to show that it is an average. The way we calculate it is we're taking the C of X that we just did and dividing that by how many wheelchairs. So dividing it by X. So 400X plus 500,000 divided by X. And notice now X cannot equal 0. We can't divide by a 0 with the average cost function. So next what we're going to do is we're taking the average cost function that we just did, and we're going to go ahead and find and interpret all these different numbers here. So the cost function of C of 1,000. So 400 times 1,000 plus 500,000 divided by 1,000 equals $900. Now, again, remember that when you're putting this in the calculator, this has to be inside parentheses if you're doing the whole thing, or you have to press enter and then divide by 1,000. So what does this mean? It costs $900 to make one wheelchair when making 1,000 wheelchairs. Okay, next we're going to look at 10,000 wheelchairs. So what happens? 400 times 10,000 plus 500,000 divided by 10,000. This becomes 450. So it costs $450 to make one wheelchair when making 10,000 wheelchairs. Okay, so let's see what happens when we're making 100,000 wheelchairs. We're already seeing that the more wheelchairs we're making, the cost is going to be lower. So this is going to be $405. So it costs $405 to make one wheelchair when making 100,000 wheelchairs. So what can we say about the more wheelchairs are made, the cost does what? It decreases. Now, but as you can see, it's $900, 450, and $405. So something's slowing it down a little bit. Um, so find the horizontal asymptote for the average cost function and describe what this means for the company. Okay, so our cost function here, this is what we're looking at right now. Horizontal asymptote, we need to look at the degrees of the numerator and the degree of the denominator. So those are the same. So 1 equals 1, n equals m. So our y, our horizontal asymptote is going to be the leading coefficients divided. So 400 divided by 1 is 400. So our horizontal asymptote is going to be y equals 400. So what does this mean for the company? It means that the cost for one wheelchair will never be $400 or under. So we can see that this is approaching 400, but it doesn't go below the 400, even though they're making 100,000 wheelchairs. Okay, that's it for this lesson. Let me know if you've got any questions. Bye.